So let me give you a very brief overview, very simple view of series, parallel, and what we call combination or network circuits. So just to be clear, a battery is made up of little cells, and we model those cells with lines. Short line and a long line. We usually consider the long line to be the positive side and the short line to be the negative side. So a couple of those cells together make up a battery. So this is pretty close to the symbol you'd see for any battery, positive and negative. And that could be a 10-volt battery, 100-volt battery, whatever denomination of battery you want. So then you have a wire, and the diagrams are usually made nice and boxy. And we go from typically what we call the positive side, and then we go back to ground on the other side. And ground is again usually called the negative or the common side. So we can actually draw in a load. I'll draw a resistor. A resistor would be pretty much just any coil of wire, or it can be as complex as a load like a toaster or anything that's actually using electricity. The simpler the better in this case, because we're using direct current since this is a simple battery. When you use alternating current, and even if you use direct current and some more active components, then you get into time delays, and that's all wrapped up into the creation of these electromagnetic fields. So we're going to hold off on that for a little bit. But this is a basic circuit. You can see I'm closing it off. And so now it's actually a full circuit. This is the simplest circuit you can really draw. You're guaranteed to have current flow. So there's our current I. Because it's closed off, this is some known voltage, we'll say, and some known resistance. If there were pretty much no resistance to it, then we'd be short-circuiting the battery. But either way, it is a complete circuit. Now, what you can do is you can actually set a resistor in series with this one. And now we have a series circuit. This is the most simple series circuit that you possibly can get. And we can call one resistor 1, and we can call one resistor 2, and we can label them, and it really does not matter which one we put where. So resistor 1 and resistor 2 might have different values. And ultimately, you can find what's called the equivalent or the total resistance. I'll call it total resistance here. So the total resistance for a series circuit is very, very simple to find. All it is resistor 1 plus resistor 2 plus however many resistors you put in line. So if resistor 1 is 10 ohms, resistor 2 is 20 ohms, then we're going to have a total resistance for the current that would like to flow of 10 plus 20 or 30 ohms. And then you can apply Ohm's law and Watt's law and anything else that you'd like to figure out the other characteristics of this circuit. So we could again add as many resistors in there as we wanted to. I could put a resistor here. As long as they share the same wire, the same path from high voltage to ground, then they are in series one with another. So imagining now that we instead create a second path. Let me pull this to the side. And just for the sake of clarity, let me pull that to the side. We just short-circuited out the battery, right? And how about we create another path here? So there's one resistor. I want to get a little clean here. Let's see. One resistor, and then another resistor. And what do we have? We now have parallel circuits, if you will, as part of this overall series circuit converted into a parallel circuit. Imagine this is closed off. So we have one path for charge and a second path for charge. Both of them see this high end. Doesn't matter which one comes first in the line here. They both see the high end, the high side of the waterfall, if you will. And then they both come around and they both share the same point of contact. They see the ground, or the common side. And so they're both going from the same height of a waterfall, very high voltage, down to very low voltage, or zero, I should say, in this case. So we have one current here, one current there, and here's actually what happens. The current comes in. Remember, these are just charges moving as charges should. And then the current actually will split. One will come here. Another will come this way. And then they're actually going to add back together again. And this is like a continuity equation. What goes in must come out. And the amount of charge that flows from this end to that end through resistor 1 and this end to that end through resistor 2 depends on the amount of resistance. Remember that we always have heard electricity chooses the path of least resistance. Well, if you short circuit something out, then all the electricity is going to flow there. If this is 10 ohms and this is 30 ohms, then you're going to have a 2/3 portion go through the 10 ohms and a 1/3 portion go through the 20 ohms. And you'll see that it divides perfectly. So now we can actually move from just a parallel circuit, and we can get a little bit more complex here. Incidentally, before we go on to that, you're asking, hey, what is the R total for this? Well, I try to avoid overwhelming you, but it's basically 1 divided by a nice little fraction. 1 over R1 plus 1 over R2 plus 1 over however many R's you actually end up having. So before we move on to anything more complex, let me show you. Let's just imagine this is the simplest you can get. Two that are actually in parallel, one with another. If this is 10 ohms, watch my math. 1 over 10 plus, if this is 20 ohms, 1 over 20. If you like mathematics, follow me. If you don't, try to follow me. This is 2 over 20. 1/10 become 2/20. And so I end up with 1 over 3/20. And because that's 1 dividing in, that becomes 20/30. Okay? And you can simplify that down. How many times does 30 go into 20? Well, if you need a calculator, here it is. I love fractions. So 6 times, and you have 2/3 left over. .67 ohms is our equivalent resistance for these. Now, wait a second, you say. 6.67 ohms? Huh. I thought we had a 10 ohm resistor and a 20 ohm resistor. Well, this is something that you can use to check. because whatever your total resistance is for a parallel circuit by itself, it should be less than the smallest resistor's value. Why? Well, think of it. You're providing more paths for this charge to flow. And so you're actually making it easier for charge to flow. You're ultimately, by adding resistors in parallel, decreasing the resistance. Okay. So keep that in your pocket. Now what we can do is we can take another resistor and you know what we're going to do? We're going to add that in series with these. And let's just call that resistor 3. All right. So all that has happened is we take the parallel resistance and then we add in the series resistance. So if this was 6.67, let's say resistor 3 is, I don't know, 30 ohms. Then we have 36.67 is our total equivalent resistance. And then we can apply Ohm's law to determine what the current is, and it's actually traveling through this battery. So you have some excellent examples here of the most basic series, parallel, and combination or network circuits.